So, hello everybody. I think probably we started recording, right? I wouldn't know. I hope. Okay. Thank you all for coming, and I'm absolutely delighted being here. Looking forward to the next 3 months, learning things from each other and advancing a subject which is actually very timely at a fast developing pace. And I'm extremely excited. I'd like to thank IPAM and the organizers, my co-organizers, and also it's probably the last talk. Many are tired, but I'm at an advantage because there were some great talks before to prepare the audience and build the background with Augusto and Dario. And so I'll be talking about Schrödinger bridges. And earlier we talked a little bit about, Augusto talked about the Sinkhorn algorithm and some of the history. So I wanted, before I start the talk, to bring to your attention this paper. We wrote this paper a few years ago with some collaborators, Chen and Michele Pavone, and has this playful title, Stochastic Control Liaisons, Richard Sinkhorn meets Gaspar Monge on a Schrödinger bridge. So much of the material, and it has some very interesting sort of historical reviews. So if you're interested, please look at it or ask me for a copy. So here, let me see, I have to do view, full screen. Okay. Oops, how does it turn? Here. Oops, no. I don't know how it turns. Oops.
I think you need to click on this. PDF. Click on the PDF first.
On the PDF?
Yeah.
Okay, yes. So I would like to thank IPAM and UCLA for the occasion, some funding, and my colleagues and students and former students, Olga, who's here in the audience, and Ralph, especially for tomorrow's talk on quantum. Today is going to be Asma and Yongxin and Michele, our two collaborators. We work quite a bit on Schrödinger bridges. Now, what I would like to say before we start, I'll tell you today about the classical Schrödinger bridges problem, the connection to optimal transport. Those things go together hand in hand. It relates to the regularization that you heard from Augusto, but there's a dimension, it goes way above, at least in the way that's perceived, and it connects to the dynamic optimal transport problem. What I would like also to bring up is that I learned quite a few things from Michele, going back 20 years on Schrödinger bridges. He was a follower of Nelson, and he worked on Schrödinger bridges even before, quite a bit. And then we started working in the it was 2010. And the first paper we actually did on Schrödinger bridges was the first one on quantum Schrödinger bridges. And then we turned back into the classical. So sometimes I always say that if you want to understand probability, ordinary probability, it's better sometimes to venture into the quantum first and then come back. It makes you appreciate certain things. So anyway, oops, I don't know what happens here. Okay, this is like this, yes. So I'm going to start very, very slowly. I understand the people, some of the participants have a varying background. So I would like to explain a few things about entropy and relative entropy, because it's very essential to what you are seeing it, and one should not be left with the impression that it's just a regularization quantity, okay? So entropy, again, I'm not going to say all that much. Maybe you have seen this quote here. Claude Shannon, the founder of information theory, he says, my greatest concern was what to call it. I thought calling information, but the word was already used, so I decided to call it uncertainty. And John von Neumann suggested the following. You should call it entropy for two reasons. First, that this uncertainty function has been used in statistical mechanics and has this name. And second, more importantly, that nobody quite knows what entropy is. So in a discussion, you have to have an advantage. So, I mean, this is, supposedly, this is a quote from Shannon. So I will spare you a discussion about the connections to thermodynamics. It goes back to Clausius. Q here is change in heat and absolute temperature and so forth, but sort of the modern day sort of way of understanding it, which has to do with information and uncertainty, comes from Boltzmann, and he thought that this was probably one of the most significant things he did, to write this expression down. KB translates unitless quantities into energy, so that doesn't matter, it's some constant, the Boltzmann constant. The important thing is a logarithm of W, and W is the number of microstates of some ensemble or structure. And the way to understand this is, let's say, suppose you have equal probability of occupying a number of states. The logarithm of the number of states is the number of bits you need to describe where you are. So if you have 4 states, right, 2 to the power 2, so you need 2 bits. So that exactly quantifies the information that you need in order to localize. And if, for instance, there is a probability of being at some state, then the proper notion is this one, okay? In statistical mechanics, you see it with a KB in front, and in quantum, we're going to see it more, and you already saw it. It's called the trace, minus trace rho log rho, where rho is a density matrix. Okay. Oops, here. So one more slide about entropy. Maybe might have 2. The way to understand this is, another way to understand it, because this is going to become handy when we talk about relative entropy, is, again, as I explained, you can occupy a place A, B, or C. You can think of it as a source spitting out symbols that take one of those values with a certain probability, and the probability of A is higher than the probability of B and C. Now, if I want to communicate to you a long word, how many bits should I send you? Okay? Now, I wouldn't want every time the symbol A appears to send you, I mean, all the symbols, every time they appear, I don't want you to send you certain number of bits that encode this particular 3 possibilities, because one is more frequent. So if the symbol A appears more often, I should use a shorter word to describe it, because it will happen all the time. The other ones that are more rare, I use longer. So if you allocate, let's say, 1 bit to this one, and the B and the C, you preface it with the symbol 1, and then you discriminate with a 0 and a 1. Then on average, you need 1.5 bits per symbol if the source produces ABCs with those frequencies. So that's the idea of source coding. And this expression, the entropy, exactly tells you the average word length to describe the symbols that are coming at you. So here it's the number of bits on average needed to store a message from a given source, to encode and communicate the signal, and so forth. And there is something also, there's a version of that which is called differential entropy, and it's integral P log P. And this is about continuous random variables. The probability is on R, for example. And there is a little bit more subtle, because to localize exactly the value of X, you need infinite precision. So the entropy is infinite. So you can say that the entropy to within an interval can be written in this way. So there's a term over here goes to infinity, and this one is the differential entropy. So that's not so important right now. But basically, the idea is you encode the word lengths. Now we are going to have a couple of slides, 3 slides or so, on the Kullback-Leibler divergence, the relative entropy that you saw already. And why is this important? What are the manifestations of this? Where does it come from? So here you have two probability laws, and you heard before Augusto explained that this is a natural way of explaining the distance between them. And you can write it like this, P log P over Q, or you can write it like this, which is more convenient when you go to quantum, even though there are many versions of it. And you can also write it like this, that's also very interesting. So you have the expected value with respect to Q of P over Q, and P over Q is some rather Nicodim derivative of one probability measure over another. And then, right. And if the two probability measures, one of them is not absolutely continuous to the other, you declare this to be infinity, okay? So this is all fine. It's some distance measure between probabilities, but why do we care about this? Okay, this is the continuous version of that. It's not so important. This could be an arbitrary measurable space, and as long as one measure is absolutely continuous with respect to the other, you write this expression like that. And we're going to see this, okay? Because we'll be interested in trajectories and paths of random processes. So let me not go too fast, okay? So you have probability laws. This is an arbitrary measure space. It could be the real line, or it could be the space of paths, all kinds of trajectories. And again, you describe the relative entropy. The relative entropy is more well-behaved than the entropy in the sense that the part of the differential entropy that goes to infinity cancels between P and Q. And this quantity here is always positive. You see where is that here? The differential entropy here could be positive or negative, because you can have a spike here, etc. Okay? But the relative entropy, whether for discrete or continuous spaces, is always positive. And it induces a nice Riemannian metric on the space of probability laws. It's a long story, and if you're interested, we can discuss more of this. Now, I would like to explain what it means, what the relative entropy actually means. So a very, very simple way of understanding it, now we're talking about discrete spaces. As we discussed a minute ago, the entropy is the average word length. The optimal code will have this many bits to transmit the information of what symbol is coming at you on average. That's called the entropy rate of a source. But if you make a mistake, if you encode based on P, but the symbols are coming from a source with probabilities Q, okay? What do I have here? Average, well, using code design, let me see here. Right, you design for Q and it's P, yes, right. So this is suboptimal. So you design, right, you design for Q. So this is kind of the word length for the per symbol, but they're coming at you at a different rate than you thought. And if you design with a P, then you get that, and this is always positive. That's a beautiful way of understanding this. It's the degradation of coding efficiency. Now, this is another thing which, these are all very related. This is another way that relative entropy manifests itself in quantify the likelihood of rare events. The probability that an empirical average, again, we can connect it to what we just discussed, but the probability that an empirical average is far away from the mean. So, for example, suppose you have independent samples from some random variable that takes values 1 up to n and is distributed according to Q. So if I press carriage return and I get 1,000 samples, and then I plot a histogram, I'm going to get this. right? If I plot a zillion samples, then it's probably going to be nice and smooth and fine, right? But if I sample n times, the empirical measure, which is exactly this histogram, may deviate from the exact distribution Q. So this distance becomes smaller and smaller when the sample size becomes larger, right? But at any time, it could be way off. Let's say I have a coin which is 50-50 heads or tails, and I toss it 100 times. And let's say 100 times I get heads. 100 times I get heads. You can't tell me that it's not 100 times heads. You say, oh, that's not likely. Yeah, it's not likely. But the probability is very small, but it happened. So it happened. What is the probability that you get a rare sample? Now here there's a little bit of technicality because you need to have a representative which is close to what you're looking. But anyway, don't worry about this so much. The probability of getting a rare event decreases with the sample size, right? Because if, for example, I have one coin and I toss it once, it will be either heads or tails. This is very far away from 50-50. It's 1-0, right? But if you have 100 of them, we'll get closer, etc. So the rate with which you're getting convergence, etc., or the probability that you get something very far from equilibrium depends on this large deviation rate function, which is the distance of the observed histogram from the typical. Okay? And a very similar thing, for that very similar reason, relative entropy is very important when we do maximum likelihood estimation. So you observe some empirical, let's say the mean and the variance, and you say what is the most likely value for certain coefficients that give me this kind of results. So in a very similar manner, you say the most likely posterior is the one that minimizes the relative entropy. Because if you have various choices and you want to say which one is, if I don't know the parameters, I want to say what is the most likely, I'm choosing the one where the probability is concentrated on, okay? So this is basically the background on relative entropy. And again, just to belabor a little bit the point, how do you reconcile statistical data? The origin is statistics. And in statistics, quite often, they had different quantities. Let's say the price of a certain stock and the price of the coffee and whatever. And they are jointly distributed. Maybe one affects the other. And then they have empirical distributions, and some of them they trust more than others. So for example, a typical situation is you have some sort of prior, and you get empirical distribution of the x and the y, and then you say what is the most likely dependence between one and the other that is in agreement with the data that I collected right now. This is the source. This is very much at the heart of what Schrödinger bridges are. And as I'll show you, it relates to optimal transport in a very central way. So from what we said before, the natural way of looking at it is you find the closest to the prior, which the marginals agree with your data. So this problem, the history of this problem in statistics starts around 1935. And the theorem that I explained to you here, which is called Sanoff's theorem, that quantifies the probability of rare events as the distance of the law that you observe or the data that you collected to the typical, this theorem, which is known as Sanoff's theorem, actually was implicit in the work of Schrödinger in 1931-32. Yes?
In this case, the P, the convex set of distributions, will have the marginals, correct marginals.
Yes, yes. So you pull from a distribution Q. You get some empirical, basically the histogram, right? Now, there is a slight technical tweaking here. You could say that the probability of Pn, your empirical, is basically minus n, the relative entropy between Pn and Q. Okay? Pn and Q. Wherever you have P star, replace Pn. Okay? That is 99% correct. The technical issue here, which is hidden in all this stuff, is that, you see, if I have a Pn here, which is, let's say I toss a coin 100 times, and I get pi by 6 times, someone gives me a distribution pi by 6 and 1 minus pi by 6. Pi by 6 is not a rational number. It cannot happen from, pulling it n times. So you have to smooth out around it and technically look for some neighborhoods and so forth. So this is, does this make sense? So for all practical purposes, Pn is the P star, okay?
And in connection.
Yeah?
Convex set, capital P, the convex set that we define, it should be a ball around?
Yeah, some ball around, yes, in suitable sense. Yes, but it's just exactly to avoid some technicalities, okay? This is all what's called, is a subject of large deviations theory. And it becomes more complicated when you talk about bigger spaces of paths, of trajectories of probability, stochastic processes and so forth. But basically, that is the interpretation of relative entropy, okay? And again, the origins in the 1935, 40, in statistics, they started looking at this problem, saying, look, here's my prior. I expect that this is going to be a relationship between these two random variables, but I have this data, and the data is not consistent. How am I going to correct it? So then they started doing, in an ad hoc way, the Sinkhorn algorithm. And I'll say a little bit more about that. You have sort of a prior, think of it as a matrix whose row sum and column sum are supposed to be something, and they're not what you think they are. So what do? You scale diagonally the rows, and you say, okay, now I match the row sum. Then, but you look at the column sum and it doesn't agree. Then you adjust that by multiplying. So you keep iterating, and they discover, oh, surprise, surprise, it converges. And they didn't know why it converges. And it took quite a while before Sinkhorn proved it for the uniform marginals. But there was a proof already by Robert Fortet in 1935 for a much more general setting. I'll talk about that, following Schrödinger's formalism. But now we're beginning looking at discrete sets. So this is all the random variables take values in some discrete set, just to keep things simple. So the form of the solution is the diagonal scaling. So the way to see this, and Augusto did it, so I'm just going to go very quickly through that. You want to minimize the relative entropy subject to these marginal constraints. So what do? You form a Lagrangian. Here is your relative entropy. The probability law has two indices, x and y. And then here you have Lagrange multipliers. You take the derivative with respect to the p. The log conveniently gives you this as the solution to the derivative being equal to 0. And then you unravel it, and you see that the posterior has to have this expression. And this expression is, if you think of this as a matrix, x corresponding to the rows and y to the columns, then this is a diagonal multiplying q on the left and another diagonal multiplying the q from the right. So this is called diagonal scaling. And again, you can read more of that. Earlier was Schrödinger and Fortet. Schrödinger, by the way, he did it in a much more general setting, and I'll come to this. He didn't have a proof, and he said the structure of the solution has to be this one because it makes physical sense. And this was his proof. And then there were several mathematicians working furiously to understand the structure of this. We're going to see how this all simplifies with a Hilbert metric and how much insight you can get. So the Fortet Sinkhorn algorithm is exactly that. You start from the Q, and the structure of the solution, there's a D diagonal left, diagonal right, and the algorithm is simple. Given a matrix Q and those two vectors, you multiply with this where the diagonal is exactly what you need so that the new matrix row sums to whatever you want to sum, and then you try to correct the columns and so on, repeat until convergence. And if the Q is all positives, convergence is guaranteed. If not, there are some, sometimes it does, sometimes it does not, and you can, yes?
I just want to clarify, I think I probably missed it. Did you have a condition of the Q that it also has the correct marginals, or there's no?
No. Q doesn't need to have the correct margin. Like, for example, suppose I give you, here. I mean, a very, very, very simple setting.
No, I know that we can derive the Shannon entropy regularized optimal transport if we take Q as the exponential of the C.
Q is any prior. So, for example, I can give you as prior, 1/2. Let's see here. What am I? No. Let's say 1/4, 1/4. Let's say 1/4, 1/4, right? And I tell you, the probability, for example, my prior is Q is equal that X is equal to 0 and Y is equal to 0 is 1/4, etc. And now I collect samples. And I get that, this is all wrong, and I have some marginals. So I'm looking for a P that Pxy, so that, let's say, the row sum, you sum over X is equal, let's say, 1/3 and 2/3. So I would like the row sum to be, 1/3 and 2/3, right? But this is not that. So if I sum 1/1, that's different. So what am I going to do? I just multiply over here by whatever, 1/3 and 2/3. And now that's correct, okay? But then someone also gives me that the column sum has to be, let's say, 5/6 and 1/6. So what I'm going to do is multiply from the right now that matrix. And I keep doing this, and it converges. So initially they didn't know why, etc. Yes, go ahead.
So when you see this slide, is it correct to interpret that when you do the regularization of Wasserstein, doing Kullback-Leibler somehow?
We'll come to this. We'll see the connection to optimal transport, where it comes from. I have to talk more about the trajectories of stochastic processes, and there's a lot more, okay? But you will see where it comes. Right now, this is just I wanted to give the idea of this, the most likely solution. So here we go as a step towards what you are asking. We're going to the Schrödinger bridge problem in the most basic form, where we're looking at a Markov chain, taking values, let's say, on a finite set, 0, let's say, to n, and you have a prior law for x0 and transition probabilities. So you expect that if you're observing a path x0 up to xt, let me just erase this thing here so that I can explain what it means. This is very, very important. The moment you see this then the rest is going to be very, very simple. So you have a Markov chain, so you're given the law, and you have at time t equal to 0, for example, x0 will be one of those values, like 0, 1, etc., up to n. Then at the next instance, t equal to 1, the indices now take values x1, will be one of those symbols again. So the probability of observing one particular path, x0 up to xt, is the probability that you start at x0, the probability you transition from x0 to x1, and so on, right? Because it's a Markov chain. Now, likewise, the posterior is going to have the same structure for a transition probability that you don't know. And maybe you can set the p0 equal to q0. And now you are observing certain marginals. So you run the experiment many times, and then you have that the probability that you start from some index x0 is something, so you are given that. And the probability that you land at some index xt is also given to you. So what you want to find is you want to find the law of the Markov chain that is consistent with these two marginals. And it's the closest to the prior in the relative entropy sense. Okay? You can think of it as a one-step transition or many-step transitions, or you might have measurements in between, you have multi-margins and so forth. We can make it as complicated as we like. But this is sort of the simplest incarnation of in discrete time of Schrödinger's paradigm, Schrödinger's bridge. So what is the bridge? You are trying to bridge the empirical distributions P0 and Pt. These are empiricals, you measure them, by postulating a different law on the paths than the one you are given. And you want the law which is the most likely. What is the most likely? The one that minimizes the relative entropy to the prior. So this is Schrödinger's bridge problem.
So the unknown over here is the transition probabilities, or is the whole path?
Sorry?
The unknown in this problem is the transition probabilities or the whole path?
You know the transition probabilities of the prior.
Yeah, for the posterior?
For the posterior, you don't know anything. You just want the posterior.
So it's the whole path that you
The
want?
whole path.
Okay.
Now, it turns out, because the update is diagonal scaling and so on, it turns out that the posterior is also the same nature, is also Markov. That's a result. In principle, you could say, well, I would like a Markov. But it turns out you get it for free. Yes?
You're assuming both the prior and the posterior are inhomogeneous Markov chains?
Inhomogeneous, yes. I think this is better to think of it, because you can ask the question, can I have one that it is, the law doesn't depend on the time, in which case the problem becomes more difficult. So, but again, the spirit of it is the same. So the step that you're going to see again and again is what's called the disintegration of measure. It's just simply that the probability of taking of a particular path, for example, of taking values x0, x1 up to xt, is the probability that you start at x0 and the margins are this, and this is the conditional of observing x1 up to t minus 1, given that you have x0 and xt at the two ends. So this is called the pinned bridge. So you pin it at the two ends, and you want to know the probability that the path took this trajectory or that trajectory. So this is the conditional, or anything in between, given that x0 at 0 is x0, and similarly for p. So, but if you write the expression for p in exactly the same way, and you stick it in the relative entropy, you see the following thing, that the expression breaks because of the multiplicative nature. And then you have over here a relative entropy between the posterior that couples the beginning to the end, to the prior, that's the relative entropy of that. And here is the relative entropy of the bridges. Bridges, the pin bridges. This quantity here, like relative entropy always, is non-negative. So if you'd like to minimize this, then the optimal solution is that you assume that this P is equal to the Q. So the pin bridges are shared by the posterior and the prior. And that is a very important insight. So the only thing you need to find is you need to find the coupling. Again, this is very similar to the coupling we're talking about in optimal transport. That's a coupling between the values of this, between the two random variables, taking values x0, xt at the two ends of an interval. Okay? So there is no optimal transport, it's just this expression here, the relative entropy. The second term is 0 when P and Q share pin bridges, and we need to minimize the coupling P0T, subject to the two marginals. So the problem we have is exactly the problem.
Can I ask you something to go back one?
Yes?
Just out of curiosity, I get this part, right? So I want to find a coupling between initial and final state, and then I want to bridge using the prior.
Yeah, the bridges are going to be the same,
right.
pinned.
In terms of what you wrote in the slide before, in terms of the single, how do I see this? So the gamma hat, those are two different things, right? Those are single steps motions. Do you see here also the gamma hat 0 until the last, before the last one should be the same?
No,
Right, no.
it's more delicate.
It's more delicate.
Yeah, it doesn't mean that this and that are all the same. It's more delicate. Okay?
So,
this is the probability law from beginning to the end.
Right.
And it factors because it's Markov. When it's Markov, it factors into two tensors, so to speak, even the continuous limit.
In this case, how would they actually look? The things must be the same, the bridges in this case.
The bridges, we're going to see it later. In fact, I have a slide which is much better in the second talk at the beginning because I review this. But the bridges, you see, in order to find the probability of what happens in between, you have to use Bayesian estimation and you have to divide by something. Right. So it becomes a little bit more tricky. But bear with me, you know.
But is it always true that you have the same pin bridges as a minimal?
The minimum is you have the same pin bridges.
Always true.
The posterior and the prior share the pin bridges, yes. Because of this thing, because of the disintegration of measure. And this is true for discrete time, continuous time, everything. Okay? Here you can define conditional probability, which in quantum we have a little bit of a problem with. Okay? So that's, okay. So, right. So here, again, this is the same thing you've seen before. If you try to find, if you look at now the transition from, into one step, let's say this is the beginning and this is the end. I just named it here 0 and 1. It could have been any t. So the coupling, the coupling is minimized. The relative entropy to the posterior is minimized. It has to be of some form. So it has to be minimized. You know, then you need to minimize the here because we're using transition probabilities. You can write the coupling as the initial and the transition kernel. So the relative entropy between those two, again, can be split. So you have here the initial and so on, right? And here, this part, there's nothing you can do about because this is the posterior. Sorry, this is the prior, and this is the posterior. This is something you measured, right? And here you have a quantity when you sum over x1 disappears because this is a transition probability, and then you have only one term. If this is a transition kernel, the summation of x1 is equal to 1. So the first quantity here, there's nothing to optimize because that's given, that's given, that's given. The second part, oops, let me see here. The second part is exactly what we saw before. You try to minimize the second part, subject to some constraints, namely you're looking for the transition law, which has the property that is stochastic, raw stochastic, and maps the given one to the terminal one, and you play the same thing like before, Lagrange multipliers, derivative, and you get that the posterior will be something from the left and something from the right. And later on, so you can think of it as a diagonal, and it turns out that this is going to be, in the language of Schrödinger, a scaling factor which you call phi 0 and phi 1. Okay? These are simply diagonal scalings on the two sides. Okay? This is a little bit, no need to worry about the notation here. I just want to, it's a symbol that you're going to see very often. Now, a brief interlude on the Hilbert metric, why we have convergence. The Hilbert metric is a very beautiful concept and goes back to antiquity, relates to the cross ratio, and was initially thought of as a way to metrize convex sets. So if you draw a line here and you have a convex set in a Euclidean space, then you take A, B, C, D, the points that, you have 2 points, B and C. You draw the red line, it cuts at the A and the D, and the cross ratio is the length of the distance BA over BC, etc. And that turns out to be a metric on a convex set. And this is called the Hilbert metric. So, again, Augusto mentioned a little bit of this. It's an extremely powerful tool. If you have a convex cone in a Banach space, it has to be pointed, then you can define a partial order, P and Q. So you say P is greater than Q if P minus Q is in K. These are all in some Euclidean space. Well, no, you have Banach space, so there's no, yeah. So then you define two quantities. So it's like this. Let me just draw this. So a picture is worth 1,000 words. So let's say, suppose we're looking at the positive orthant, okay? The partial order is this. So for example, if I have a point P here and I have a point Q here, right? So you say that P, what do you say? Q is greater than P, right? Now, one of those quantities is the infimum of how you can scale. So if you scale, for example, P, and you move it here, or you move it here, let me see, what do you do? 1 second. You need, let's look at the first one, lambda bar of PQ, right? So if you scale Q, right, so here is lambda Q.
Sorry, but your P and Q there is different than the P and Q here. I think you want to switch the P and Q.
1 second, lambda, so lambda Q, no. So you scale Q, lambda Q. So if lambda Q, if lambda is taken, let's say, to be 1/2, so lambda Q is here, then, right, then for this lambda, you have that lambda Q is less than P. Do I have it right?
Lambda.
All right, I think okay, 1 second.
It's fine, then you're just doing them under bar.
The other one, yes, yeah. So in any case, you just move the cone so the one encloses the other. So if this P and Q are positive definite matrices, for example, P and Q, you look at the eigenvalues of the pencil, lambda Q. So you see what kind of a scaling you can do so that when this inequality breaks down. And you have, so the lambda, if P and Q are positive definite matrices, the lambda here and the lambda upper and lambda lower are the top and the lowest eigenvalues of the pencil. So this, oops, what did I do here? And these are the two important examples. Hilbert defined this, and then we have Berkhoff and Bushel, 57, 73, that proved some very, very important theorem. So the important theorem is this, that if you have a P, pi, which is a positive monotone homogeneous map between cones in Rn, monotone means x less than y, means pi of x is less than pi of y. Homogeneous, it applies. We're not going to need this. We're only going to have homogeneous of degree 1. So if it is homogeneous of degree 1, then automatically the amplification of pi in the Hilbert metric is less than 1. And if in addition it's linear, then you can put an upper bound of this in terms of something called the diameter of pi. So the projective diameter of pi is the diameter of its range. So you have the supremum of the distance between two elements in the range. So roughly, and this is the most interesting case for us, is that if pi is a stochastic matrix, a matrix that has all the entries positive, then the diameter is always finite. Because you're not going to have this, the Hilbert metric, if you remember, weighs the ratios. So if both quantities are finite, the ratio is finite. So as long as pi maps the cone into the interior, we automatically have contractiveness, strict contractiveness in the Hilbert metric. Okay?
Sorry, what is the Hilbert metric for your positive matrices?
For the positive matrices, we're going to talk more about this. So for positive matrices, the pi is a Krauss map, is a trace-preserving, totally positive map.
Even in the classical case, if I just want to look at the classical case, right, like the Sinkhorn one.
The Sinkhorn one.
Yeah.
So the Sinkhorn one, for example, in the example I gave before, so you have pi is, let's say, some transition probability. So you have here, let's say, 1/2, 1/2, and 1/3, 2/3, right? So this maps the positive cone, right, r plus 2 to r plus 2. This is strictly contractive in the Hilbert metric. The idea is that if you have a probability vector here, what you're going to see is that if you have two vectors here, they are mapped to be closer.
So there's a Hilbert metric in R2.
In R2.
With the cone being, okay.
In the Hilbert metric in R2. So if you have two probability vectors here, their images are closer. Basically because this thing here equalizes and gets closer to the equilibrium, so to speak, okay? It's not difficult to intuitively understand why this works. But it's very interesting, that you have a very precise expression. You have that this is strictly contractive as long as certain conditions hold. And then in the quantum case, it's very difficult to test for those conditions, but yeah, we'll talk about this more tomorrow. Let's see, until what time I'm going? 5. Uh-oh, I have a lot of material. I'm a little bit, okay. So, all right, so I'm going to go a little bit fast. So right. So you start with a stochastic metric, row sum to ones. You have two probability vectors. And the Schrödinger's theorem, which he didn't prove, but it was proved later in different forms, is that there exists a suitable scalings that a certain system of equations holds. So in the case where we have t is equal to 1, it's basically the diagonal scaling that we saw earlier. Let me see a little bit how. So think of the transition from let me write something here, because this is so you are given a matrix. Now I write it as pi transpose because the entries of this, let's say pi x0 xt, is the probability that you transition from x0 to xt. Right? The probability that x0 is equal to x0 and, this is xt is equal to xt, given that x0 is equal to x0. Okay? This is the notation. So if I want to write it as this acting on column vectors, then I have to have the forward map with the transpose here. So what we would like is to reconcile the two marginals, pi t. So we can explain the form of that as diagonal scalings, but it's very insightful to look at the Sinkhorn iteration in the following way. You're looking here for a vector, phi 0, and another vector, phi 0 hat, phi t hat here. This is Schrödinger's notation, though in continuous spaces. Here is phi t. These are column vectors of the same size as pi 0 and pi t. And they are such that the entry-wise product of phi t hat, so this is like a sure product, entry-wise, agrees with this one. And here, the entry-wise product here, phi hat, agrees with this one. Okay. So basically, you start here with a probability with any vector, any positive vector. You map across. Then you go down by dividing entry-wise, because this is given. If you know this one, then the other one is, entry-wise ratios. Okay? That becomes an isometry in the Hilbert metric, because you always have ratios. We can play with that. This is an isometry. This thing here is multiplication with the matrix pi. You get to this one, then you divide to go there. That's again an isometry. So the composition of these maps is contractive. So the composition from the phi hat 0, phi t, phi, etc., and then this is the next one, is contractive in the Hilbert metric, and it converges. And what you can see here is the solution here. You have, let me see. So if you throw in a vector p0, and you divide by the diagonal with entries phi 0 inverse, then assuming that you have converged already, you divide by a diagonal with entries phi 0, you get phi 0 hat. Phi 0 hat already maps to this one. And here, if you multiply with a diagonal with entries phi t, then you get pi t. In the reverse direction, if you throw an identity vector, and here you have what do you have? You have the adjoint of this map. So this is phi t. Is a diagonal matrix with phi t on the diagonal. You throw in a vector with all ones. You're going to get phi t. Then you get phi 0. Oops. And then the adjoint of this, which because diagonal is exactly the same, will give you 1. So as a result, the pi transpose multiplied by d phi 0 inverse, and on the other end by d phi t, is a row stochastic matrix that maps pi 0 to pi t. And row stochastic because the sum of the rows gives you 1. This construction is basically everything, and you will see it repeated in various guises, okay? The thing to see here is that this stochastic map is sort of enhanced by some scaling on one side and scaling of the other side that's kind of simple. In the quantum setting, you're going to see that sort of a Krauss map will be enhanced by the diagonal scaling will be multiplication by a Krauss map with only one entry. Okay, it will be exactly very similar. Okay. So
There is small typo there. It should be on the right. On the left, it should be xt, right? Summation over xt.
say that again.
Just above in the bottom left corner. Yeah, summation is over xt, right?
Yeah, this is sum over xt. Yeah. Sorry, I mean n and xt, etc. All right. Okay. So again, the ranges of those, if you assume they are still in the interior of the cone, both the forward map and the adjoint are contractive. The vertical things, which are sort of divisions by this, I call it with d. Those maps are isometries. So the Schrödinger has a solution up to scaling.
Can I ask just one very quick thing? So if you do one loop, it means that you try to fix one marginal, the second one, and then
yes, well, it's somewhat, yes. I mean, it is basically this. The iteration is embedded in this.
Okay, because I don't see it.
The Sinkhorn iteration is embedded in this. That I mean, if you go through one iteration, you get closer because you multiply on both
The
sides.
gamma t would be one marginal, the gamma would be the other marginal,
Yes.
fixed point would be.
Yes. Yeah. Yeah. I mean, we can. Yeah. I think it's a much cleaner picture for what follows to look at it this way. So yeah. So here again, I'm going through the motions to show that if you take two vectors in the Hilbert, the distance between two vectors is the same thing as the distance between their inverses. So the inversion or scaling both vectors with the same coefficient, this type of things are isometries. All right, so then this gives you basically the theorem that you have. And then if you peel this back into the Markov chain that we had before, you try to reconcile the marginal from the beginning to the end. Then the same picture here can be if you have a Markov chain with many steps, so you go here, phi 0 hat, pi 0 transpose. Then you have phi 1 hat you look at the propagation, here pi 1 transpose, and so forth. And then here you have the final. Pi t is the product of phi t and phi t hat. So again, the same kind of argument holds true. And what you see is that the posterior has the following form. So the posterior is pi 0. And then we have here phi 0 inverse transpose. Let me think. Yes. No, the pi 0 will come on the other side, right? So we go like this. So the forward map is going to be the last one. Here we go from here. Pi 0, and then a diagonal with phi 0 inverse, diagonal with phi 1, diagonal with phi 1 inverse, pi 1, diagonal with phi 2, right, and so on, diagonal phi 2 inverse, etc., and we get to the last one. So this is going to be the posterior. This is the same as the prior from the beginning to the end, and diagonal scaling adjusts that. If you have many steps, the scalings propagate through, and you get a Markov law again, because every transition kernel is just scaled in the same way. Is this clear, or?
But this would come already from the fact that the pin bridges are the same.
Yes, this comes again. It's another manifestation of the fact that the pin bridges are the same.
And who proved that?
I mean, this is implicit even in Schrödinger's.
So
He didn't prove, no. He stated, and I'll explain it later, for the continuous time case, that this problem, basically what I refer to here as a Schrödinger system, this is in discrete case. He didn't write that, but basically, effectively he wrote this, because the way he explained it is by dissecting in terms of space and time. So effectively he did that, and he wrote down that the system has to have a solution. And the system has sort of some integrations this way, and it has this product structure. Okay? And he claimed it, and the first proof is due to Fortet.
But Fortet also proved that the pin bridges are the same for...
They didn't have exactly that insight. He proved that the algorithm converges. The story...
Just to say, the fact that the pin bridges are the same comes from the disintegration theorem. So that he wrote earlier, the disintegration.
No, but the disintegration, so who proved that? Because that's the claim that second part is greater equal to 0, right?
This is trivial because once you can disintegrate the path measure, then you're done. You see that the optimality requires that it just has to be 0.
But so long as you know that the inequality is true, right? The greater equal to 0 is true. That I agree. It's trivial once I have that inequality.
It's the relative entropy of...
First of all...
Also, that second part is also a relative entropy.
Yeah, exactly.
Oh, okay.
So the relative entropy of whatever the path measures disintegrates into relative entropy of the marginals plus the relative entropy of the
Okay, somehow I thought the formula was different, but okay, I'll ask you.
Let me say the following. Now, it's very difficult to say who proved what and when, because Schrödinger stated that this system has to have a solution. Fortet had a very complicated proof of showing that there is going to be a limit there's going to be a solution to the system. 35, there were many people that worked on that, but the problem was not understood as a large deviation problem until the 80s. And it was Fulmer I'll explain more when we go to the continuous time case. Give me a little bit of time because time is running very fast. Oops, no. Okay, here. So this is the structure. So now we go to continuous time. And whatever we discussed so far, it basically comes alive here, but is in the background because, so Erwin Schrödinger wrote a first paper in 1931, followed by one in 1932. The title of the paper is very telling, on the reversal of the laws of nature. So he was interested in explaining Schrödinger's equation in a more fundamental way. So he postulated the following experiment. This is a thought experiment. He says, consider a cloud of n independent Brownian particles. So I open a box here that has oxygen molecules. I open it and there's a concentration. And this, from all I know, they're Brownian particles that will spread all over the room. 5 minutes later, I measure them. I try to see where they are somehow, and I find them here. You can't tell me they're not here because I measured it. So he asked the question, what is, given you have empirical measures, something unlikely happened, surprising thing happened. These are not compatible with the transition mechanism that you are given. They're not Brownian. Something happened. This is not the law. Particles have been transported in an unlikely way. And he asked the question, of the many possible ways, which one is the most likely? He wanted to find, at the level of the particles, how this density went from one end to the other. So here is the picture. This is a Schrödinger bridge with two endpoint marginals specified. And basically, schematically, he wanted to interpolate in a way that reconciles the two marginals, and the new law is the most likely. So if you start from this distribution, for example, and the prior law is a Gaussian sort of diffusion, you expect a minute later to be a little bit more flat. However, you measure something different, and you wanted to find out an interpolation of the one-time marginals that is meaningful. So this is the problem of large deviations that he posed, and it was only understood in 1988 by Fulmer that this is actually exactly the thing we discussed in the previous slides. That you have empirical at the two end points, and you would like to minimize the relative entropy. And that's Schrödinger's problem. So let me very, very quickly, I have until what? Until 5? Huh? Yeah. Until 5, okay. So a very, very brief about optimal transport. I'm not going to bother you here. You have seen this before. The memoir sur le double remplay. Gaspar Monge, moving from one point to another. Okay, my French is it's late in the day, so all right. And we have the Wasserstein metric. Here we're only specializing to quadratic, and you would like you like to meet the two marginals. You need the transport man that pushes one to the other. This is what it means to push one to the other if they have densities. You all know this thing. And you have the Kantorovich regularization that you don't care about a map, but you want sort of a joint that has the correct marginals. That is Kantorovich's idea. It says, I don't care if there is a mass because I might have to split it. So now this problem here is a linear program, and he developed Kantorovich's duality theory and all that in order to solve this problem. He got the Nobel Prize for it. Now, if it happens that the marginals are nice and you don't need to split the mass, then the joint has support on a very thin set, which is precisely the Monge map that you were looking for. Right? The original problem of Monge is very difficult because it's nonlinear in the T. You don't know even how to handle this. This one is very simple. And if it happens to have a very nice solution and the densities are absolutely continuous in suitable sense, then you get the transport map as the support of the joint probability. There is a lot more here. This is nowadays we know a lot more about the structure. Of course, this is the Benamou-Brenier formula. That basically can be understood in the following way. If you have in Euclidean space 2 points, this is a high school exercise to show that the minimum of the square of the velocity for a curve that begins here and ends there is exactly equal to the distance between the 2 points. If you have 2 points and you want to go from here to here optimally, you have to go on a straight line with constant velocity. If you accelerate and decelerate, you get this integral becomes more. When you substitute this in the expression of Kantorovich's form for the Wasserstein metric, you get the Benhamou-Brenier formulation where you minimize the average kinetic energy over all particles. So the particles have to agree with each other, find who goes where, and then they move accordingly. There is a beautiful Riemannian structure. You're going to hear a lot more in this talks about this. And maybe I should just skip this quickly. This is the autocalculus that you can define. Here's the space of densities. And this is the tangent space. So perturbations of rho that retain the integral have to integrate to 0. Of course, you can ask the question, what if rho is 0 at some point? Let's leave all these technicalities. So this is functions that are integrated to 0 are intuitively the tangent space of the densities. Now, the beautiful insight of Otto was that if you have a perturbation and you would like to incrementally move in a direction, then the best you can do to minimize an expression like before is to move along a gradient. So you need to solve this some Poisson equation. And so there is a correspondence between perturbations and velocity fields, which are in the form of gradient. And such velocity fields now bring in a Riemannian metric in the space of densities, which is this. You integrate the inner product of velocity fields against the rho, and the Wasserstein distance has this nice, it's a geodesic distance with respect to this metric. So there's a lot of structure placed in the background. We're not going to need all that much, but I wanted to say it. I don't think in 3 minutes I can finish, but so here is a bird's eye view between optimal transport and Schrödinger bridges. If you start from you put a particle at x and you allow it to diffuse, this is Brownian diffusion and you get some distribution at the end. If you pin it at the beginning and the end, that's called the Brownian bridge. So the condition, now there you are very interested in the conditional probability of taking values in the middle, and we're going to see more of that tomorrow. If you try to ask the question, what is the most likely path? That if I start here and I end up there, the most likely path, the one that concentrates the most of the measure, is a straight line. It's exactly the same as the optimal transport from x to y. It's a straight line. If I condition, so the Schrödinger bridge is a soft conditioning at the end point, where you say, I start here and I want to soft condition on a probability that is not the typical one. So this is a Schrödinger bridge condition at the end. And this is the Schrödinger bridge condition at both points. Okay? If you try to solve the same problems with optimal transport, the correspondence to this is like that, and the correspondence to this one is like that. And here, all the jitter is due to the diffusion. If you crank the diffusion to 0, this solution becomes that. So the limit of the Schrödinger bridge is the optimal transport. Okay? So that's kind of a high level. So again, I explained this here quickly. This is conditioned on both ends. This is conditioned at both ends. The pin bridge is like this. Okay? The most likely path, the most probability mass in a neighborhood is in the middle. This is conditioned on, comparing when you condition on both ends to condition at the end, and so on. So this is a soft condition, and this is the comparison, exactly what I told you. Let me take another 3 minutes, okay? So some theorem Schrödinger bridges, and Leonard's paper is a beautiful reference. This is exactly what we discussed before. You try now to write the relative entropy, but the space here is much bigger. It's paths. It's like C01 or C0, right, C01. And the marginals are those. Again, you can disintegrate the measure. And exactly the story that we had before. The relative entropy is the relative entropy between the couplings from beginning to end. And this is T0 and this is T final. The notation keeps changing, I'm sorry. All right, and the other thing which has to be set to 0 and it's equal to the whatever the prior you have. So, and Schrödinger posed wrote this system, actually that's exactly what he wrote. He said the density of the density along the path has to factor as a product of two functions, and these two functions has to satisfy some forward equation and some backward equation, and their product is exactly rho 0, rho 1. This is exactly what we have here. So the hat propagates like a density, and the phi propagates like an observable. It's a dual. Their product gives you the two marginals. So basically, at the level of Schrödinger, with the example that I had before, you have somehow to factor the beginning distribution into a product and the end distribution into a product. These are all unknowns. These are the phi's and the phi hats. The phi hats propagate with the forward Fokker-Planck equation, the phi's with the adjoint, and at the two ends, they are equal. So he discovered this, 1931, doing exactly what we did, Lagrange multipliers. And then he was stunned by this because it has a very much of it looks like quantum mechanics because the density becomes the product of something. They are not so here is one second, what did I do here? Yeah, so he saw in this the wave function and its adjoint, even though these are not exactly the same, okay? And okay, here is exactly the proof of convergence for the Schrödinger system. It's verbatim what we saw before. You have here the diffusion, and the iteration here is contractive in the Hilbert metric. Now, there are a lot more, but I think it's getting late, so I probably should, let me see if I can, there are different ways of viewing this. So you can, this is a very beautiful expression. So if you look at the relative entropy, and if you have the prior, let's say it's the Wiener measure, and you have a posterior which is absolute continuous. The absolute continuous to the Wiener measure corresponds to the law of a diffusion with a drift. You have to trust me on this, okay? Because if the diffusion coefficient here is different, you will be able to tell one will be more jittery than the other, and the two laws will not be absolutely continuous. So the only way that there will be absolute continuous if there is a difference in the drifts. And the law of P with respect to W, the relative entropy, and that's called Yassanov-Cameron-Martin theorem, can be expressed exactly like this, is the average kinetic energy. So you see over here elements connecting bridges and optimal transport in many ways. So you can write a stochastic formulation of Schrödinger's problem where you have exactly the Benamou-Brenier expression, except here you have the Laplacian. So, and if you have a coefficient here, epsilon, that goes to 0, then this in the limit becomes 0 and you have optimal transport. You can write it also in another way, which is you can get rid of you can redefine the velocity and absorb this into a new velocity here. And this is also very interesting because now you have a continuity equation. That's still the Schrödinger problem. You have a continuity equation matching the marginals. And the course is a kinetic energy plus a Fisher information component. So there are very many, let me see. I think probably I have lots of applications here. Let me see, these are different Schrödinger bridges. You can play a very similar game if you like to have higher order dynamics. So you can say, I want to minimize not kinetic energy, but acceleration. And there are interesting twists to that, even at the level of optimal transport. So here is a recap, and I probably should stop here because everybody's tired. It was a long day. So the Schrödinger bridge problem and OMT have analogous formulations. I hope I gave you a little bit of gist of that. I'll start tomorrow's lecture with repeating a few things. You minimize the cost of transporting, minimize cost transversing from beginning to end, and one is deterministic, the other is stochastic. Can be solved with iterative methods due to the Hilbert and Sinkhorn. And now the OMT provides Riemannian geometry, and there is beautiful work of Jordan, Kindler, and Otto that relates the flows to entropy production and dissipation, and many things we're going to talk more during the next few months in the workshops. So with that, I would like to thank you for your attention.